Andrea started our PhD in 2020. As you know, something kind of small happened in 2020. It wasn't a really big deal. Yeah, just some small pandemic, you know. And as you can imagine, it's extremely difficult to start a very hard journey in the middle of such a difficult and complicated situation. But Andrea really rose to the challenge. She's done a lot of really amazing work. She's published in our most competitive venues, including RSS and IJR. She was even nominated for Best Paper, which is really fantastic, and we're really proud of her. In addition to all of her really wonderful contributions to science, she's also a hugely influential person in our community. As you can tell by all of you being here, she's won numerous awards for her contributions to the community, including the Ambassador Award, and she's really done a lot for us. And I think in addition to being able to do great research, being able to contribute to the community is a really huge deal. I encourage everyone to follow in her footsteps, and we're really proud of her, and we're excited for what she's about to present today. Just a little bit of housekeeping. Andrea's going to do her thesis presentation for about 45 minutes. We're going to have a few minutes for open questions. That's when you get to grill her. This is the last time you'll be able to grill her, so, you know, really grill her.
Thanks.
Then we're going to have a closed session where we'll be grilling her, and then it'll be closed session with deliberation, and then we'll welcome her back in for the final decision. Sounds good? Questions? No? The floor is yours.
Awesome. All right, thank you, Nima, for that introduction. And thanks to my committee for being here, and to all of you virtually in the room and who will watch later. To begin this presentation, I want to take you all through an example of a robotic system that operates in a highly structured environment as a contrast to the unstructured environments we'll be talking about for the rest of the presentation. This is a FANUC system implemented by Remtech for packing small tubes. FANUC is a global leader of automation for manufacturing. This system has two main components: a side to load the machine that seals the packs, and a side to unload the machine. On the loading side, product tubes are arranged into a single-ish layer on the conveyor belt. Then, two robots with custom tooling pick and place the tubes into packs. However, if we slow it down, we can see that the robot has trouble with pick-and-place operations when there are two tubes stacked on top of each other. The robot tries again and picks a different tube. On the unloading side, a custom pick-and-place system removes packaged products from the machine and separates them to match the retail trays. A different robot picks up the rows of packages and places them into another machine, which moves the product onto a station to prepare them for distribution to retailers. When we zoom in, we see a drop package of tubes underneath all the different machines. This package likely missed its slot in the next machine, dropping beneath the conveyor belt. This system operates in what we call a highly structured environment, where engineers have designed and validated extremely precise systems to achieve high repeatability and throughput. Even in these specialized and highly structured systems, we still see errors like failing to pick up a tube or dropping a package. Now, I don't know about you all, but nothing in my day-to-day life is this structured. Let's consider the increased complexity of the diverse and dynamic spaces in which humans operate. We call these unstructured environments. When roboticists think about general robotic manipulation, they are often driven by societal needs in unstructured human environments. For dexterous tasks in these environments, uncertainty is all but guaranteed. We think about completing dangerous or strenuous tasks, such as spacewalks or physical labor that often leads to overuse injuries. We think about automating tasks found in home and manufacturing settings, such as shelving or manipulating textiles. We think about facilitating personal and rehabilitative care, where robots can improve patient outcomes by providing automated assistance to human experts. And we think about assisting with tasks like cooking and cleaning, allowing individuals to retain more independence in their day-to-day lives, despite varied mobility and dexterity stemming from disability. While these applications are broad, they are underpinned by the notion that general robotic manipulation requires dexterity under uncertainty. We need to be able to reason about many different types of uncertainty to move away from the industrial standard of highly structured environments. And there are many different types of uncertainty pertinent to object manipulation, including uncertainty in how objects are being held, impacting how we use them. Uncertainty in how objects are shaped when they're partially hidden in clutter, impacting how we pick them up. And uncertainty in what objects are made of, impacting how much force we apply to them. Failure to reason about any of these types of uncertainty can lead to downstream task failure. My dissertation specifically focuses on uncertainty in grasped object pose, which we disambiguate with proprioception and tactile feedback. Many sensor modalities are used to estimate the pose of a grasped object, like the hex key shown here. The state of the art in state estimation for robotic manipulation often uses vision-based sensors. These sensors use cameras and depth sensors in a passive sense, meaning that they can constantly get information as long as they're on. Liken this to your eyes. In a well-lit room, you'll see if your eyes are open. This also means that if something blocks your view, you will no longer gain information about it, and we call this occlusion. There are also touch-based sensors, which are an active sensory modality. This means that information is only gained when the sensor is touching something, and you can liken this to your fingertips. You'll only feel pressure when you're touching something. We also often use force torque sensors, which measure the pushes and pulls exerted on the robot using strain gauges or other technologies. Finally, algorithms in robotics often use proprioception. Proprioception is the robot's sense of where its joints are, which is usually measured with joint encoders. Different state estimation methods in the literature use various combinations of these sensing modalities. In contrast to proprioceptive and tactile-based approaches, there are many existing vision-based approaches to state estimation. However, these approaches are fundamentally limited by occlusion, which is an inevitability in contact-rich interactions. Let's look at 3 examples. The goal of this first method is to accurately detect the presence or absence of contact points between a robot gripper and an object. From this view, it's plausible that there may be contact at the green points highlighted on the gripper. However, from a different view, it becomes clear that there's a gap between the gripper and the box. The alignment of the gripper and the camera is what leads to this inaccurate detection of contact points. The goal of this second method is to estimate the poses and sizes of unseen object instances in a scene. In this failure case from a challenging camera angle resulting in partial occlusion between objects in the scene, we see that both the camera and the cup are not detected at all. The goal of this third method is to estimate the poses of objects with known geometry in a scene. In this cluttered tabletop, we can see the instability of the pose estimation on the right side as different objects move into and out of view, such as the mustard bottle or the pitcher. All 3 of these examples showcase how occlusion can impact the fidelity of vision-based state estimation for manipulation. There are various existing methods for state estimation using proprioceptive and tactile sensors, and we'll go through 2 examples here. The first method, the contact particle filter, uses noisy joint-level proprioceptive signals to reason about external force torque applied to the surface of a robot. There are other approaches that use particle filtering methods to estimate contact between a robot and its environment, but generally these methods consider single robot cases or known in-hand object pose, but an uncertain environment. This second method uses a visuotactile sensor called the GelSlim 3.0, which uses an internal camera to provide a high-resolution view of the contact interface. This method for estimating in-hand object pose and others like it often perform best when the object renders a richly featured tactile imprint. If you were to grasp the hex key without the bend initially between the sensors, the pose of the hex key would have much more uncertainty and existing methods may fail. The existing literature on this topic leaves a niche for us to fill. How can robots use contact cues for in-hand object pose estimation? To help answer this question, today I will introduce research I have conducted over the course of my PhD. In chapter 3 of my dissertation, I introduce a method to simultaneously estimate contact location and in-hand object pose with a bimanual robotic system. To address residual ambiguity in object pose after a single interaction, I extend this method to consider sequential interactions for in-hand object pose estimation in chapter 4. In chapter 5, I build upon this framework by introducing proprioceptive uncertainty to the in-hand object pose estimation method. This tackles a real-world issue that we experience with our robots. Finally, in chapter 6, I revitalize and open source a powerful visuotactile sensor and conduct a user study to verify its reproducibility. We'll start by taking a dive into chapter 3, which details our method for simultaneous contact location and object pose estimation, and we call this method SCOPE. In this image, the robot on the left is holding a probing tool, while the robot on the right is holding a wrench tool. The probing robot has brought the tip of the probe into contact with the wrench, as we see on this zoomed-in view. Our inputs are force torque feedback, measured at the wrist, and the robot joint states Q. The goal of this method is to take an initial distribution of in-hand object poses and use the inputs to accurately estimate the ground truth in-hand object poses. Notably, we estimate the pose of both the tool and the probe. To do this, we make 4 key assumptions. First, that objects are rigid with no geometries. Second, that we have access to robot proprioception and wrist wrenches. Thirdly, that contacts are point contacts and are well approximated by the point contact model. And finally, that probing actions do not result in relative slip between the object and the probe. Our method works by leveraging 2 complementary particle filters. The first particle filter is over contact location, and the second filter is over object poses. By bringing 2 objects into contact with one another, we can iteratively exploit mutual information between the known object geometries and detected contact events to simultaneously estimate contact location and in-hand object pose. The higher level filter is over object pose, which we refer to as scope. It uses the contact location estimation results of the underlying contact particle filter for grasped objects, or CPF grasp, to estimate object pose. And we'll first take a look at CPF grasp. The goal of this method is to find the contact location and applied force torque that best explain the force torque experienced by the robot. In this optimization problem, RC is the unknown contact location, gamma EE is the measured force torque experienced at the wrist by the robot, gamma C is the unknown force torque at the contact location, and the adjoint is the matrix that maps a force torque experienced in the contact frame to the equivalent force experienced in the end effector frame. Additionally, we are subject to 2 constraints: that the contact locations are on the surface of the objects, and that the contact wrenches are inside the friction cone. More explicitly, contact locations are points in R3 that we consider to be point contacts. Force torque wrenches are 6-dimensional vectors where the first 3 entries are forces and the last 3 entries are torques, and the adjoint transformation is a 6x6 matrix. Now let's take a look at our constraints. First, we consider the friction cone, FC. Any force inside the friction cone represents a sticking contact, and any force on the surface of the friction cone represents a sliding contact. We define the friction cone at a point on the object surface and align the cone axis with the surface normal at that point. We constrain our contact wrenches to be on the interior of the friction cone, or sticking contacts. To make this problem more tractable, we will take the polyhedral friction cone approximation. Using the same cone as before, we define unit vectors F to create the polyhedron. Each of these vectors is assigned a constant alpha, which we constrain to be greater than or equal to 0. This ensures that our contacts always push and never pull. Finally, we generate the resulting wrench by summing the products of alpha and F. However, this problem is still non-convex due to the bilinearity in contact location and contact wrench. Instead, we'll use CPF grasp to propose contact locations. Now, our goal shifts from finding both the contact location and applied force torque to being given a candidate contact location and finding the force torque applied to that point that best explains the force torque experienced by the robot. Here, we also introduced the problem sigma M, which is a matrix of calibrated sensor noise. This allows the method to be robust to noisy force torque estimates obtained in the real world. A simple approach for contact location particle initialization is uniformly sampling from the tool surface. This approach results in smaller faces being sampled less frequently than larger faces. However, these smaller faces may be intended to make contact with the environment, like the opening of this wrench. If there are no contact location particles on these faces at initialization, it is unlikely that the filter will converge to them because the particles would have to traverse high error faces to get there. To address this, we formulate a tool segmentation algorithm that segments the tool into faces and then samples particles from each face of the tool. We define a face as a group of points that have similar surface normals and are spatially close together. To find groups of similar surface normals, we use k-means clustering of unique surface normals. And after grouping by surface normal, we use dbScan to further separate faces that share the same surface normal but are spatially distant from one another. Our tool segmentation approach ensures better convergence properties for CPF grasp than random initialization. By using this initialization method, CPF grasp achieves lower position error and resultant wrench error than random sampling up to 50% density. While it takes a few more iterations to converge, our tool segmentation approach still reduces computation time because it requires far fewer particles. Here's what CPF grasp looks like in action, starting from initialization and progressing through several iterations to resolve the contact location to about 0.5 millimeter. Now that we've introduced the mechanics of CPF grasp, we'll take a look at the details of scope. In order to initialize object post particles, we introduce two constraints for a valid grasp. Firstly, the object must be within some distance of the center of the gripper, and we call this the center constraint. Secondly, the object must not be in collision with the robot geometry, and we call this the collision constraint. Both constraints must be satisfied to accept the sampled object pose as a valid grasp. And notably, we make the rigid grasp assumption here. To score object post particles, we use 4 scoring metrics that formalize underlying contact mechanics. The penetration loss penalizes object post pairs that are in collision with one another because we know that there is no penetration in the ground truth contact. The contact consistency loss penalizes object post pairs whose estimated contact locations are far apart because we know that they should be at the same point. The force alignment loss penalizes object post pairs whose estimated contact forces are in different directions because we know the forces from a mutual contact point should be equal and opposite. Finally, the wrench loss enforces that the contact location resolved by CPF grasp explains the external force torque experienced by the robot, which is shown here. On the left, CPF grasp gets as close as it can to the true contact location. However, the object post particle, which is the orange silhouette, does not include the true contact location. On the right, this object post particle will have a better score in this metric because the true contact location is on the surface of the object post particle. For 5 independent probing actions with the wrench tool in simulation, we see that the translation error is within 2 centimeters and the rotation error is within 5 degrees. However, there is high variability between actions that dramatically impact the pose estimation error. And this leads us to the next chapter, focused on disambiguating in-hand object poses with multiple interactions. As I mentioned just a few slides ago, there is high variability between actions that dramatically impacts the pose estimation error. For some actions, the distribution over object pose is much tighter after an action than it was at random initialization. But for others, the distribution over object pose looks about the same after an action as it did at initialization. For this reason, we want to string together multiple interactions to gain information from them sequentially. To facilitate this, we need some framework for memory and consistency. So let's take a look at a simple 2D case to formulate the memory metric. Let's consider this first action where a blue probe is poking an orange object. For simplicity, we'll assume the object post particles are distributed laterally, like so. Now let's consider a second action where the probe pokes the orange object on the other side. For simplicity, we'll again assume that the object post particles are only distributed vertically, like so. If we consider these actions independently, we can see the phenomenon we showed on the last slide, where one action results in a larger distribution of possible object poses than the other. However, if we consider these actions together, we can shrink the possible space of object pose solutions. Let's consider 2 object post particles, shown here with dashed outlines. Using our memory of the first contact location from the first action, we can score each object post particle by using the distance between the object's surface and the previous contact point. In this case, the object post particle on the bottom is a better solution because the distance between the contact point from the last action and the object surface is smaller than for the object post particle on the top. We can then flesh out this idea into a full consistency framework, and we'll walk through this step by step. First, we run scope for one action and score the object post particle pairs. Here, the wrench object post particles are shown in orange in the left column, and the probe object post particles are shown in blue on the right column. Then we take the next action, and here, importantly, we do not add any noise to the system as we usually would between scope steps. This means that we can directly compare the highest scored object post particles from one action to the next action. To do this, we'll use a subset of our scoring metrics that does not include the memory loss. It does include the penetration loss, contact consistency loss, force alignment loss, and wrench loss that we introduced previously. If the consistency score for object post particle pairs jumps up between one action and the next, we assume that the object post particle pairs do not represent the ground truth state of the tools. In this case, we do not use the result of the previous action in our memory loss moving forward. If there is good agreement between the actions, we add the result of the last action to our contact cloud, which we then use in the memory loss going forward. This framework allows us to build up results of previous actions that we can use to reason about in-hand object pose over sequential actions. And in simulation, we take sequences of 5 actions with the wrench tool and 4 actions with the hex key tool. Then with these action sequences, we ran multi-scope and tested 2 tasks with the object pose estimation results. In each task, we used the ground truth tool pose, which is here shown in gray, for collision modeling, while we use the estimated pose, shown in green, for planning. The task with the wrench was to surround a screw head, and the task with the hex key was to insert into a screw head. Both tasks had just under 2 millimeters of tolerance, and each of these tasks succeeded in 8 of 10 trials in simulation. We also tested this in the real world with the wrench tool with slightly larger tolerance. We took the sequence of actions shown here, and then we tested this planning method in the real world with the wrench tool, and it succeeded in 5 of 5 trials. Moving on to chapter 5 with this multi-action framework in hand, we'll look at a very common assumption that we make in our work, that we have access to robot proprioception and that the proprioception is low error or even error-free. Over the years, we've used various tools to calibrate our bimanual robot system. However, our calibrations are usually local to a specific part of the robot workspace. As we've expanded into a multi-action framework, we've noticed that it is difficult to calibrate our robots globally. Other Franka users have also noticed. The forum is full of people expressing their frustration that the robots are difficult to calibrate with respect to the world frame of the end effector. And my personal favorite line in response to one of these queries was simply, "There is no way to calibrate the robot." So here's what I mean by this. On the left is a picture of what the robot state was in the real world, and on the right was what the robot model filled by encoder values thought the robot was doing. And this was after calibration. So we decided to break out some high-resolution depth scanners to investigate. When we've talked with other robot users, the first question we are always asked is, are you sure the bases are properly located? To answer this question, yes, we're quite sure. What you see here is the model of each robot base in yellow, aligned with a high-resolution depth scan from a photo neo scanner in blue. In order to accomplish this, I dramatically cropped the scene point cloud to reduce the noise, and then I performed a coarse mapping using Ransack and fine-tuned using ICP. Having those transforms in hand, we're able to view the full scene and confirm that our robot bases are calibrated to the resolution of our depth scanner, which is less than 0.5 millimeter. After performing the space calibration, we are confident that the errors in the robot model are configuration dependent and in the kinematic chain past the robot base. Using our high-resolution depth scanners, we collected several scans at random robot joint configurations and aligned them with the robot model based on the joint encoders. When we look at the 2 samples of full robot scans, we can see this configuration dependency. In the scan on the left, the robot model closely aligns with the real-world scan. However, on the right, we can see that the arm is drooping below where the robot model expects it to be, and we need some way to quantify this difference. In order to learn a joint state mapping, we collected a small batch of 34 joint state samples that were representative of the probing actions we take in our method. For each sample, we recorded the joint state measured by the robot, QRobot. We also recorded a point cloud of the scene using the photo neo scanner. To find the optimal joint state QOptimal that explains the scene point cloud, we use PySwarms to implement particle swarm optimization. We initialize the swarm about QRobot and limit the particles to be within 3 degrees of each joint in QRobot. Our cost function is the inverse of fitness between the scene point cloud and the surface point cloud of the robot model given the particle. Fitness measures the overlapping area of 2 point clouds where a higher number is better. And this helped us quantify the error we are seeing on the robot platform. For a sample of 10 random joint states, we found that the minimum end effector error from these samples was about 1 centimeter, while the maximum error at the end effector from these samples was almost 4 centimeters. The measured robot joint state QRobot and optimal joint state QOptimal are then used to train a residual neural network, Phi. This network takes the joint state QRobot and is trained to predict the difference between QOptimal and QRobot. We then use the predicted joint state, QPredicted, in place of the measured joint state for the probing arm everywhere in our method. However, even after this calibration, we can still expect that our robot model will not perfectly represent the ground truth. After this calibration procedure, the maximum error of the end effector from those same previous samples was 1 centimeter, reduced from almost 4 centimeters. For the samples that had lower error initially, the error was reduced to less than 1 centimeter. Therefore, we still need to reason about uncertainty in proprioception measurements. To do this, we'll look to Rudolph's work on the probabilistic robot kinematics model. This method uses uncertainty at each joint to build up a configuration-dependent distribution of possible end effector poses using the product of exponentials method for forward kinematics. We have reproduced the results of this work as we show here with the Panda robot in a planar case. In each subfigure, the highlighted joints have a standard deviation of 10 degrees applied, and we show samples of possible end effector poses sampled from the resulting distribution at the end effector. The sampling-based method integrates well with our existing framework. Mismatch between the robot model and the real robot can be very influential on the success of the loss metrics we introduced for CPF grasp in Chapter 3. And to show why this is the case, we sample several end effector poses for the robot arm holding the hex key here. The ground truth tool pose for each robot is again in a light gray color. And even with the small amount of uncertainty added here, there are now tool geometry pairs with no contact between them or with penetration between them. Without considering robot proprioception in our object pose estimation framework, our method may try to bridge these gaps by altering the object pose to enforce contact or reduce penetration. However, because these errors are configuration dependent, the object pose has no ability to consistently explain the errors across several probing actions. You'll also notice that each sampled end effector pose has a corresponding color. To integrate these end effector pose samples with multiscope, we use the log likelihood of each sample to calculate the weight of each sample in the set of sampled poses. I'll spare you the math for time's sake, but as a refresher, this proprioception uncertainty is folded into the penetration loss, the contact consistency loss, the force alignment loss for CPF grasp, as well as the memory loss for multiscope. Finally, we tested this in the real world with the hex key task. As opposed to the previous methodology without proprioception uncertainty, the only thing we coarsely calibrated here was the location of the insertion point in the world frame. Now, the intuitive next step for this framework is the integration of another sensing modality, such as vision or tactile sensing. This leads us to the next chapter, which focuses on the democratization of tactile sensing. The market for tactile sensing is small and relatively unstable. There are 3 main types of tactile sensors that are available to purchase commercially: force torque sensors, visuotactile sensors, and biomimetic sensors. Force torque sensors measure the pushes and pulls exerted on the sensor, and these sensors can either measure at a single point or several points, like the contactile sensor shown in the middle. Visuotactile sensors use internal cameras to view contact interfaces with high resolution and typically have a flexible contact interface. Biomimetic sensors use human biology as inspiration, such as these biotact sensors that have small ridges like fingerprints to detect vibration patterns. However, the market for tactile sensing is small and relatively unstable, and to illustrate this point, SynTouch ceased its operations earlier this year after about a decade of producing these sensors. Visuotactile sensors have a lot of advantages for reasoning about contact-rich manipulation. Firstly, they provide a high-resolution view of contact. Then, the material deformation gives information about shape and shear. These sensors rely on image processing methods, which have made leaps and bounds of progress in recent years due to advances in computer vision. And finally, they're robust to imperfect manufacturing methods, which means they're amenable to being made in a lab or research setting. In the Manipulation and Machine Intelligence Lab, we use several visuotactile sensors. We primarily use a soft bubble gripper developed by Toyota Research Institute and the GelSlim 3.0 developed by Ian Taylor at MIT. Because my in-hand object pose estimation framework utilizes a rigid grasp assumption, I chose to experiment with a GelSlim 3.0 sensor. Neither of these sensors is a true rigid grasp, but the GelSlim 3.0 more closely approximates it. This sensor does not exist in a vacuum. There's a lengthy history of development of this technology, starting in 2009 with the first benchtop version. Notably, other form factors of tactile sensors predate this gel-based visuotactile sensor. We see evolution into smaller handheld and benchtop versions, and then a break into fingertip-based sensors. Over time, these form factors also decreased in size and explored other functionalities until about 2022, when the GelSlim 3.0 was released as the first open source gel site sensor, and the GelSite Mini was commercialized. Since then, there have been tens of new papers from research groups all over the world with new form factors of gel-based visuotactile sensors. However, a critical component of the GelSlim 3.0 sensor has recently been discontinued by the manufacturer, leaving one of the only open source options for the sensing technology unbuildable. A hallmark of tactile sensors is that they are fragile and that they degrade with use. As we began to use the sensors that MIT was kind enough to send us, we saw this in action. Paint on the gel peeled away and the gel itself tore. The LEDs went out, which dramatically changed the sensor images. And additionally, we noticed that the sensors themselves were quite flexible. This flexure caused the sensors to bend away from grasped objects, which results in the tactile imprint tapering away and confusing algorithms that expect the sensors to be rigid. These issues prompted us to try and make the sensors ourselves so we could repair and continue to use them in our research. However, in this process, we identified several pain points with the manufacturing of the GelSlim 3.0. First, that they are no longer maintained. Secondly, that they had discontinued critical components. Then, that the CAD models were overfitted to specific manufacturing methods and that they had limited capacity for modification. Finally, that the manufacturing instructions themselves were incomplete and that there was an unstandardized calibration routine for each individual sensor. To address these pain points, we introduced the GelSlim 4.0 and make the following improvements. As an overview, here's a diagram of the critical components of the GelSlim 4.0 sensor. These files have been rebuilt from scratch to allow full access to the design history, which enables users to tweak tolerances to suit their manufacturing capabilities. To consolidate the sensor, I redesigned the sensor body to be one single component, which eliminates 3 heat set inserts from the original design that were quite difficult to place. Additionally, I reduced the number of press fits of the sensor body to simplify manufacturing. I also make it easier to integrate the camera and lock it in place inside the sensor body by securing it with fasteners rather than a press fit. Finally, I revised the lens of the sensor to reduce its cost from $50 to 13 cents, allowing it to be treated as a consumable component. All the CAD files are available in both SolidWorks and Onshape. And this is important because SolidWorks has an expensive license, while Onshape has a free service tier and a free education plan for students and educators. In addition to the CAD files, comprehensive written and video documentation of GelSlim 4.0 manufacturing processes have also been released on our website. We have also been able to reduce the sensor flexure of the GelSlim 4.0 by thickening the sensor body, which was difficult to do with the GelSlim 3.0 CAD model. We use SolidWorks simulation to perform a finite element analysis on each sensor body to characterize the reduction in sensor flexure. We examined the resultant displacement from the simulation, and we found that under 10 newtons of applied force, the GelSlim 3.0 sensor body deflected a maximum of about 1.5 millimeters, while the GelSlim 4.0 sensor body deflected a maximum of 0.14 millimeters. We additionally found that the simulation of resultant displacement failed for greater than 17 newtons of applied force to the GelSlim 3.0 sensor body, and this indicates that the part would likely fail catastrophically in real life. It took 100 newtons of force applied to the GelSlim 4.0 sensor body to reach a maximum deflection of about 1.4 millimeters. And this is important because our Franca Emica Panda hand can apply about 55 newtons of grasp force, while our WSG 50 gripper can apply about 80 newtons of grasp force, both of which exceed the expected maximum load for the GelSlim 3.0 sensor. Because simulation of 3D printed parts is notoriously difficult, we also tested sensor flexure in the real world. We 3D printed the GelSlim 3.0 and GelSlim 4.0 with the same Mark forged Onyx filament and infill settings, then assembled the GelSlim 3.0 sensor body. We mounted each sensor to a table and slowly added mass to load it in the same direction as grasp force would be applied. We loaded each sensor with about 18 kilograms or 40 pounds. When the GelSlim 4.0 survived this loading, we added some body weight for fun. And the sensor began to slip out of the clamp and break the table. So we stopped there. While the GelSlim 3.0 plastically deformed under the initial 18-kilogram load and was unrecoverable, the GelSlim 4.0 was undamaged after putting body weight on top of the initial 40-pound load. And I would happily mount the post-test sensor on a robot for real use because it was in such good shape after the test. The release of the sensor design is accompanied by some fundamental algorithms: depth estimation and shear field estimation. The depth estimation uses a learned model rather than an analytical solution, as was previously deployed with the GelSlim 3.0 sensor. And this has the advantage of removing the camera calibration step for each sensor, which makes using it a lot more practical. We also include various representations of shear information in the shear estimation library, such as the time derivative of the shear field shown here, which is a useful representation for tasks like peg insertion. These methods were implemented by William and Samantha using data that Sam collected with various objects and sensors. All right, so now we're gonna do like a little bit of a pivot, and I hope the volume works because I forgot to test it. But by show of hands, how many of you have ever taken part in or heard of the classic intro to computer science activity where you're tasked with providing instructions to make a peanut butter and jelly sandwich? Nice, okay. So you'll recognize what's about to happen in this video, but for the rest of you, this activity is often used to give new computer science students an introduction to the literalism of programming a computer. It will do exactly as it's told, even if that's not exactly what you meant.
Get some peanut butter. Get some jelly. Open the peanut butter. Get a butter knife. Put the butter knife in the peanut butter. Take the butter knife out of the peanut butter.
You did it wrong. No.
Take one piece of bread and take the butter knife that has the peanut butter on it and spread it all over the top of the piece of bread. That's the top.
I mean the sides.
Squirt some on another piece of bread. Take the butter knife, rub it all over the top of the piece of bread.
I quit. You're not making any sense.
All right, a little bit of levity here. So a lot of people will recognize the pattern we just saw in their roles as educators, parents, engineers, designers, etc. You've spent so long on perfecting this design. Why can't the user just use it right? In this case, the user is being deliberately adversarial, but in many cases, the user is just trying their best with the skills and experiences that they bring to the table as individuals. For this reason, we user tested 3 tasks in the GelSlim 4.0 manufacturing manual with 17 novice users from various STEM backgrounds to ensure the reproducibility of critical components. It's important to highlight here that user studies are not typical in this domain. While many sensors claim to be user-friendly and accessible, almost none have conducted formal user studies to ground those claims. We tested 4 versions of the manual while iterating between each version. And we selected 3 tasks for this study that are critical to the successful fabrication of the sensor. We chose a soldering task for task 1 because surface mount device soldering can be an unfamiliar and intimidating skill that may dissuade new users from making the sensors. Participants each made 1 LED harness. Next, we chose a polishing task for task 2 because the quality of the lens heavily impacts the final sensor images. Participants each polished 1 acrylic lens. Finally, we chose an assembly task for task 3 because while it is possible to pay for turnkey fabrication of GelSlim 4.0 components, it is impossible to purchase a fully assembled sensor. Participants each assembled the GelSlim 4.0 from pre-made components. We also surveyed participants to learn about their prior experiences with relevant manufacturing skills. Soldering experience is relevant for task 1, sanding and polishing experience is relevant for task 2, and assembly from instructions is relevant for task 3. We found that participants had a wide range of prior experience with these methods. We used a NASA Task Load Index, or NASA TLX, survey for this study, which allows users to rate their subjective workload on 6 different scales: mental demand, physical demand, temporal demand, performance, effort, and frustration. These ratings are accompanied by a weighting procedure that allows us to convert the survey results into an overall workload score out of 100 for each task, where a lower score is better. In addition to the NASA TLX, we also used observations of participants completing the tasks, as well as direct feedback from the participants to update our task instructions. Observations and feedback from both participants with and without relevant prior experience were valuable for updating the instructions from various user perspectives. As an example observation that resulted in an update, a participant with no prior soldering experience in version 1 did not know to clean the underside of the solder stencil and consequently failed to fabricate a working PCB. These instructions were made more explicit in the next version. As an example of direct participant feedback that resulted in iterative updates across task versions, several participants, including a participant in version 2, requested better qualitative signs for progressing through the lens polishing task. The graphics and instructions were iteratively updated between participant groups to incorporate this feedback. And this is the graphic that, after several revisions, was added to the release version of the manufacturing manual to highlight the different stages of the polishing task. Overall, 13 participants successfully soldered LED harnesses, 15 successfully polished lenses, and 16 successfully assembled the full GelSlim 4.0 sensor from parts. Shown here are the average workload scores for version 3 participants, with the soldering task being rated 29.9 out of 100, the polishing task being rated 36.9 out of 100, and the assembly task being rated 16.8 out of 100. These results felt surprising to us and motivate this study very well, because I personally struggled to learn how to make the LED harnesses from task 1 with the previous GelSlim 3.0 instructions. I expected this task to have the highest workload by far. However, what this study showed us is that more consideration was needed in order to properly communicate endpoints for the preparation of the acrylic lenses in task 2, which was something that personally came second nature to me. Ultimately, this finding reinforces the idea that engineers are not the users and that formal usability assessment is necessary for devices that claim to be easy to use or accessible. The full manufacturing manual for the GelSlim 4.0 is now available on the project website with comprehensive written and video instructions to manufacture the sensor, and we hope to see people adopting and contributing to it soon. That brings us to the end of my talk. In summary, in this dissertation, I contribute 4 works that help to answer the question of how robots can use contact cues for in-hand object pose estimation. In chapter 3 of my dissertation, I introduce a method for simultaneously estimating contact location and in-hand object pose with a bimanual robotic system. To address the residual ambiguity in object pose after that single interaction, I extended this method to consider several sequential interactions for in-hand object pose estimation in chapter 4. In chapter 5, I built upon this framework by introducing proprioceptive uncertainty to the in-hand object pose estimation method, which tackled the real-world issue we were experiencing with our robots. And finally, in chapter 6, I revitalized and open-sourced a powerful but visuotactile sensor and conducted a user study to verify its reproducibility. The work you've seen here has been published or is under review in these venues. And now we come to the part where I will probably cry. I'd like to thank my committee for their time and feedback that's helped shape my dissertation, and I will be reading off a script so that I can get through this in one piece. Thank you to Nima, my advisor. I am a member of NEMA's very first cohort of PhD students. I'm the first to pass my qualifying exam, earn my embedded master's degree, pass my dissertation proposal, and now defend my dissertation with NEMA as my advisor. Accordingly, we've navigated many challenges together, and I have learned a lot from working with you, wherever you are. Where are you? Over there, okay. Both in terms of technical and non-technical skills. When I was arriving at Michigan, I was still voraciously print debugging and stacking for loops like a Django world champion. And being able to work hands-on with full systems in your lab has tremendously developed my skills and habits in so many areas that will benefit me for the rest of my career. Thank you to Dimitri for making your lab's equipment and expertise so accessible to me and also the rest of Mint Lab. The guidance you and your students have been able to provide to us over the years has helped to jumpstart our lab in really awesome ways. And it's been delightful to have so much collaboration with your group. Thank you to Leia for supporting the human factors side of my work. You are inspiring to me in so many ways, and it has been a privilege to be compassionately mentored by you. And finally, thank you to Rudolph, who's online, for serving as an external member of my committee. We first met at IROS in Kyoto, where he was the chair of the session I was presenting in. And Rudolph planted the seed of an idea then, which slowly grew for about 1.5 years and blossomed into chapter 5 of my dissertation. I've greatly appreciated your support and feedback on my work. I listed my lab mates in alphabetical order here so that I cannot be accused of favoritism, but we all know that my favorite lab mate is Samantha. So thank you to these guys for truly just being there every day, good days, bad days, in and out of lab. You guys have been tremendous to work with, and I'm gonna miss you so much. I also want to shout out my day ones, Mark and Mikkel. This picture was taken by Selfie King Mikkel on our first day all together in the lab on October 13th, 2020. We quite literally built Mint Lab with sweat, blood, Mark's in particular, and tears in our first year. You guys absolutely rock, and one of the things I'm most proud of at my time at Michigan is the student culture that we 3 built from the ground up in the lab. I'm excited to pass the torch to the younger students to see what amazing things you do in the years to come. As Nima said, I'm a very community-oriented person, and this is a very long list that probably doesn't even include all the organizations that have supported me over my PhD. Both at UM and beyond. They have also fueled me with snacks, which are very important. So Gender stands for Gender Diversity in Robotics, which is a club that I co-founded with Wami, who I believe is online, Dr. Wami. So thank you to all the organizers that have helped keep that afloat, including Wami, Elizabeth, Emily, Melody, and Justin. Queer in Robotics is also a branch of the nonprofit OSTEM that I founded a few years ago. And this is an external one to that helps queer roboticists all over the world find community in their robotic spaces. And so I'd like to thank Mauro, Raj, Roberto, and Rashira for helping me really get that effort off the ground, as well as from Queer and AI, which is the parent organization, which helped us figure out all the little fun things of working through a nonprofit, including Willie and Pranav. I'd also like to thank GelSlim and Wire, who've supported me at Michigan, and Robotics as a whole, but specifically several people, including Jesse Grizzle and Brent Gillespie, as well as Denise, Dan, Damon, Kimberly, Christina, Renee, Teresa, David, basically everyone who makes this department such a wonderful place to be. And also the other groups that kept me sane, including my community from my racing team in undergrad, CIA Buggy, and all the various soccer programs that I've participated in, including at Carnegie Mellon and all the way back to my high school, who I think some of my coaches are watching. In particular for CMU women's soccer, to letting me meet Hannah Linus, who at every point reminded me that I totally could do robotics, and supported me since I met her in 2015. I also want to take this opportunity to shout out that I have published some non-research papers, including launching Queer in Robotics, which is published in the Robotics and Automation magazine, to let the community know how we're supporting LGBTQ+ students in robotics. I'd like to thank my family for constantly supporting me and bullying me for being a nerd just enough. Thank you to my parents, Anna Maurice, for driving out from Pennsylvania, even though my dad is in a booch. My parents are both educators, and they've taught me so many things. From my dad, I get my incredible stubbornness and dedication to always doing what's right, even when it's hard. From my mom, I get my sense of wonder, as well as the mental block that prevents me from turning down any challenge ever. Unfortunately, my little sister Renee couldn't be here today because she's busy educating the next generation of scientists as an 8th grade math teacher. However, I owe her a huge thank you for listening to me vent literally every single day. And in true sister fashion, I will now claim that I am the taller sister because she isn't here to prove otherwise. She may look taller in this last photo, but she was wearing heels and she regretted it. My grandma Bobby also traveled here today from Ohio. The supply of chocolate caramel she's provided were definitely a major factor in fueling my dissertation. I have many other family members either online now or who will be watching later that I owe thanks to for their support. Uncle Sean and Aunt Erica, Aunt Gail, Uncle Neil, Uncle Eric, and Aunt Heather, and several of my cousins, Eleanor, Preston, Jude, Ramona, Ryan, Claire, and Ellen. I know that I've missed a lot of cherished moments with you all while I've been in Michigan working on my dissertation, and that even the times I have been able to visit, it's often cut short or distracted by my academic work. I'm looking forward to enjoying a work-free holiday season where I finally talk about something other than how little sleep I've been sleeping or how badly my robots are behaving. There are also 3 family members that I miss dearly who could not be here today. My mère Denise, Papa Laszlo, and Grandpa Bert. I've carried tokens of them with me throughout my journey. My mama's jewelry and paintings, the pen my papa loved to make, one of which will be used to sign my paperwork today, and the beautiful notebooks from Grandpa Bert's office that I filled with my research notes. For those of you who don't know, Peter and I met right down the hall, 6 feet apart, and moused up in 2020. When Peter moved to Boston in April, he left his PhD regalia in my closet, and he said I'd need it soon. His unwavering confidence in me on my best days and my worst days has given me the energy to just keep pushing. He also reminds me to eat dinner, go outside, drink water, go to bed before 4 a.m., you know, all the little things you forget to do as a PhD student. Peter, I can't thank you enough for not only being the backbone of my mental health for these past few months, but also for being the best adventure buddy ever. Our greatest adventures are yet to come. And finally, my friends, more than any individual face or moment, I want to showcase the vibrancy of my life because of the incredible people in it. I started my PhD in August 2020, not knowing a single soul in Ann Arbor except for Alex Moy, Rolled Hearts, who I couldn't even see because of COVID restrictions. And since then, the friends I have made have joined forces with the friends supporting me from afar to help me get across this finish line. Thank you for keeping me as sane as possible, even though full sanity wasn't in the cards and we all know it. I'd like to thank Dia for traveling from Detroit and Sophia for attempting to travel from New York City to be here today. They round out the group chat with my sister that is the outlet for all my greatest joys, sorrows, and stupid questions. I'd also like to thank Hirsch for traveling to be here from Florida and being a trustworthy and skilled confidant in some of my most challenging moments. I truly couldn't have done this without you all, and you are all my village. Finally, I would like to thank the dogs in my life for reminding me that I need to graduate and get a job so I can afford to have a dog of my own. To anyone struggling with grad school, I recommend having friends and family that own dogs because they won't solve all your problems, but they'll do quite a bit. And with that, I will wipe my tears and accept public questions.